Hello and welcome to another Toybox audio video demonstration video. This particular video we are going to just do a little deep dive into the Tangle Oscillator, which is the flagship product oscillator block from the recently released Tangle Pack. This Tangle Oscillator is quite interesting. I've not seen anything like it before. So let's have a quick look at it. What is it? It is a kind of sine syncing windowing oscillator is the best way to describe it, with no functions happening on the raw waveform. We get a beautiful simple sine out of there. As we can see, I've got some visualizations up on the right here so we can have a look at the output. It's just scope one will be interesting when we start getting into the windowed things. But so what this does is it basically cycles the sine, kind of syncs it, loops it, repeats it. As you can see, the kind of fundamental stays, but we get this overtone, very clean overtone happening over the ever more complex you can see how the waveform becomes more rich. And I mean, when we're doing subtractive synthesis, what we want in subtractive synthesis is beautiful, rich waveforms to subtract from. And this is one of the great aspects of this oscillator, is that it's kind of instant high harmonics, high frequency information, interesting high frequency information, which you can keep or filter away. But fundamentally, it's complex. So let's have a look at what kind of complexities we can get out of it. So what we've got here is you might recognize this from our other blocks. It's a wave shape. It's a kind of oscillator core. Now the repeat function only is applied to the sine shape. So if we put that back to 0 again, we'll look at the sine shapes. We've got a cosine here, triangle from the top. Let's go from the top as we should really. We've got a sine right at the start, beautiful clean sine, going into a triangle, and then a saw wave, and a pulse, and a cosine, a triangle, and a kind of ramp, inverse of a saw, and into another cosine. Now, only the cosines and sines are affected by this repeat function. So let's just observe that. That's what's happening there. We cycle through that waveform, you know, and squeeze it into the same kind of space as one cycle. So we get the tone. But, so what we've got is we can up that repeat rate from one of the cosines or sines and fade between these more complex harmonically rich waveforms. And so the kind of idea, the core principle is that only the sines and the cosines are affected by this repeat function, and which gives you the ability to sit between, say, your saw wave and your cosine near the end, and to apply the repeat function to the cosine part of the faded waveform. So, I mean, as you can see, you've got a kind of saw wave with like a sine function on the rising ramp. And I mean, some of these noises, this kind of thing might be familiar to you already if you've worked with synced sines on your soft synthesizers. So that might be familiar to you. Here's where the kind of magic happens. It's the between the phases, it's the between the waveforms where you've got multiple kind of waveforms crossfaded. So if we just pull that back to 0, this is between the cosine and the square, the pulse wave. So we can modify that with our synced sine window. got all kind of loveliness out of that. So that's just the basic waveform itself, with no kind of additional manipulation, just the kind of repeat function. Now what we've got is this windowed idea, which allows us to apply a window to the synced sines, and as you can see here, we've got we've got a ramp. It even says it in the little knob here, in the little button here, a ramp window. So if we turn up the sine sync, we can sort of see this ramped window appear. I mean, as you can see, if you add those two together, they're kind of DC offset, but you could probably see that together that would make a ramp. Those sines are kind of curved into a ramp wave shape. And you can see if I switch to the other option, which is the triangle, you get the windowed sines in a kind of triangle shape, which kind of softens the sound a little bit. Interesting for, you can hear the ramps a bit of a harder edge and the triangle's kind of softer. You can obviously still hear the sort of overtones of the synced sines over that. So that's the basic functionality of the oscillator. On top of that, though, we've got this other beautiful set of complementary features which you can use to mangle your shape. So I mean, we'll do FM last, because FM is a beautiful thing and we all know what it sounds like, but we're just going to look briefly at these other shapes. So we've got the bend up here, which stretches, kind of bends the waveform shape within itself. As you can see, we've got this repeating function here. If we look up at the scope window up here, we can see these repeated sines, and the bend feature is kind of squeezing. So we've got more of the sine up to the left edge of this kind of whole wave cycle, and less to the right, because we've bent it as such. If I can pull it back, you can see the kind of sine waves evenly distributed amongst that little bit of wave space. And then we push it the other way and we can bend all those synced sines in the other direction, towards the other side of the wave shape. And this is nice. This is where some great stuff happens. So we've got no amplitude shaping. Let's just put on the ramp shape just to give it... See what it does there. So what it does, it kind of shapes it, kind of filters it a little, and you can see those waveforms squeezing and stretching up in the scope up to the right there. And then we have the pulse width function, which does a pulse width operation on it. It's similar to a bend, but it's a kind of linear, moving reshaping of that waveform. And again, it's kind of after all the sync processing, the sine sync processing, so we can width modulate the sines within that kind of wave shape. Oh yeah, bubbly. So that's the pulse width function. And that was the bend function as well. Now the final option here is the FM, and here's where kind of the joy happens. There's even more joy to be had, as we all know, in the world of FM. So at the moment we've got nothing plugged into the FM socket, so there's some internal functionality that's been added to this oscillator, so that when you turn the FM up, it does something. It's not just doing itself to itself, or like nothing, basically. So what we've done is there's a few oscillators, internal oscillators have been added to the feature in case nothing is plugged into the FM input. So in phase modulation mode, it's an oscillator. I think it's just a sine wave running at the same pitch as the specified frequency that we're playing at the time. And as you can hear, That does great stuff. We add a little bit of chaos here, all the way up to, oh yeah, that stuff. So we pull that repeat down a bit, and kind of just want to show you the spaces we've got here. There's some great kind of broken territories. Look at the way that waveform exists. There's a lot of enharmonic, noisy information towards the start of it, and it's curving out. It kind of sounds quite rhythmic and engine-like. And then there's this, whatever the hell that is, just bending that shape around. This is just a phase modulation, FM kind of circuitry that we're adjusting here. Obviously, I mean, this is all just like great digital. Look at that. This is, oh yeah. I mean, it's airing on the unstable kind of arena of analog circuitry. It's kind of unstable, but because it's running at such a high rate internally, it behaves like this. So if we pull the FM back down again, let's see what else we've got. Let's reset the bend and the pulse width, and keep the repeat on. Sort of, there's a little bit of interesting harmonic information there, and we'll just flick through these FM functions. The frequency, the kind of pure FM modulation, the sort of frequency modulation. Obviously, phase modulation is adjusting the phase. And this is actually going to be adjusting the frequency, so wobbling around. I think we've got an oscillator that's kind of 3 or 4 octaves above the fundamental. We wanted it to be instantly kind of interesting harmonic stuff that gets added if you just up it in this mode. So have a listen. It's kind of, this is just one sine wave. Let's just make sure that we aren't bending that at all. So yeah, I mean, listen to that, sounds like a frequency. It's 3 or 4 octaves above the fundamental. And obviously lots of interesting harmonic information up there that we can then complicate even further with the repeat function. Oh, the kids are going to love this. And dogs, and the cats, and all the rats that use ranges beyond ours. Hearing ranges beyond ours. Let's just chop it down 3 octaves, 4 octaves. I think that's very interesting. So that's frequency modulation, like I say, 4 octaves above. We've got this phase rectified, which is the same oscillator, the same kind of oscillator and same frequency, a sine, I guess, but rectified, so it's not going between 1 and -0, it's just between 1 and 0. And that has its own domain of FM joy. I mean, well, you know, it's phase modulation, but a rectified oscillator adjusting the phase. And I mean, some of them get unstable quite quickly. Obviously, it's like just white noise. But you can clean it up just by reshaping the waveform a little bit, kind of pushing it towards the end, pushing some of the noise towards either end of the shape. Squeezing it in and kind of revealing another. Oh, look at that! That's a nice little bit of movement there on the scope. I just love all that stuff, complicated stuff at the top that's just like, where is that coming from? So let's put that back on again so we can hear the raw signal. And frequency rectified again, although I'm pretty sure that this frequency is a lot lower than the frequency used for just the normal frequency modulation for this setting. I mean, it's useful because it instantly gives you, let's just get all that stable, high additional information to filter when you hit the filter which obviously there's no filter on here because I want to show you the raw, unadulterated, high-frequency information that's coming out of this blasphemous oscillator. So let's just flick through these again. Here we are at feedback. Now, this is interesting because it's kind of similar to what the phase modulation does, because that's the same frequency just coming back into itself, but just in the phase of the internal oscillator. But this is kind of rooted externally to the internals. It's kind of outside and then back in again. Whereas this setting, FB, is internal to the ILO process, and the ILO process is the kind of analog emulation kind of high oversampled environment that's kind of doing the analog stuff. So the feedback is actually more stable. It sounds similar to, so that's a kind of, we can hear that. I mean, it's a sine wave initially, and it's been FM'd unto itself to turn into a saw wave. And kind of, as FM experts here, as we all know, that's what happens when you do that. So let's put it back on phase and see what happens when you do that. So we can see, and it kind of turns unstable. There's still a note there, but there's a lot of other noise on top of that. But with the FM, because it's doing it internally, the routing is kind of bypassing external data modification or something. That all sounds like rubbish words, but ultimately, for this FB setting, the feedback is internal to the ILO circuitry, not external to it. And I feel like I've just said that already, but basically it's a cleaner kind of feedback. As you can see, I've got it on maximum, and we haven't got noise being introduced. It's just an unstable sawtooth that's doing crazy things up here, as you can see. Nothing wrong with that. But what happens when you... So we get like beautiful things happening there. Oh. And depending on the way we approach a waveform. So this feedback function is kind of, you can get, let's do complex stuff. And it kind of holds it kind of stays stable, more stable. And if we were to do that with the phase, that just goes to noise quite quickly with a kind of harmonically complex waveform, whereas with the feedback, you can still hear the kind of fundamental frequency underneath all that beautiful other stuff. And the last two are sample and hold. The last two kind of functions here are sample and hold. And which is, it's just doing a sample and hold, just holding the frequency when the internal oscillator is triggered, when the sample and hold function is triggered by the internal oscillator. So that's obviously tracked by that internal oscillator is tracked by the coarse and the fine. And I've got a bit of a War of the Worlds sound coming in my head. So it's kind of, it's degrading, basically. It's going to be adding anti-aliasing and kind of dirty harmonics that you might find familiar from the world of digital FM from over the years. I think the first, wasn't the DX1 and the DX7, they were kind of 12-bit. I don't even think they were 16-bit, weren't they? So you've got, the aliasing that happened as part of the sound generation was just part of the sound. You got used to it. It was part of what you experienced. And nowadays we have this super high sample rate FM, and it's kind of clean. And part of the appeal for one of the other functions in this particular oscillator is the dirt. We want to bring back a little of the digital dirty history, the dirty history of digital. Maybe that's a documentary or something. But so that's kind of the sample and hold function. It's just sort of samples and holds the signal So these complex high frequency harmonics become kind of steadied, and then you've got a hold function, which is, how is that different? Sampled and held whenever the FM input is positive, and if input is positive and left unchanged, it's negative. Oh, well, there you go. So when the FM input is positive, the signal is held, and it's not held when the signal goes into negative. So it's kind of letting half the frequency, half the signal through. Again, breaking it a little bit. And all these kinds of, all these FM functions respond really well to the squeezing and stretching and pulse width modulation of these waveforms. I mean, I'm always going to go for a bass noise, so you can hear that stuff up there. Okay, aren't those knobs lovely? There's some great knobs there. The final function here, I'm going to stick that back on phase modulation, so we get some cleanliness back back again. So what we've got down here, let's just bring that back to a sine wave. So what we've got here is this final little function here, which is the kind of lo-fi mode. So by default, normal, no kind of degradation of the signal. But like the old equipment, we thought it might be a good idea, and it is quite cool. It works very well. Some get really amazing vocal sounds out of the DAC conversions here, but these are basically, DAC converters that emulate low bit conversion functions, and I think it's just the DAC emulation and the kind of different rates of emulation. I think there's one here, lo-fi, responds really well to I mean, you know what I mean. I just want to go. You know what I mean? All that stuff is really great. And then there's a load here. They're just sort of, I don't think they get gradually worse and worse, but I mean, that's quite a bad one. Quite a low res one. But I believe the DAC's kind of tracked by the incoming pitch. So you obviously aren't limited in frequency when you sort of... The frequency of the note you're playing will describe the bit rate and the sample rate, whatever kind of reduction is going on, which will then kind of change the shape of the upper harmonics and all that kind of stuff that's generated, or what gets filtered, or what gets aliased back again. So, you know what I mean? Oh my goodness, what is happening? Oh, look at the shape of that. I mean, there's like vocally stuff. Oh, I'm just getting really ugly now. Okay, what I wanted to show quickly was the other... so what we've got here is this synced sine function that is at the settings at the moment. I've showed you there's no windowing. It's just the simple cycling of this. Oh, I did show you the ramp functions, the ramp and the triangle functions. Now what we can do is we can put our own function there. Okay, I apologise for that possible jarring edit, but let's carry on where we were. I think we were at this point. We are looking at the repeat functions of this wonderful little Tangle Oscillator and the windowing, amplitude windowing of each of these wave cycles. So as we understand, these sine waves build up, but only really populate the space of one wave cycle, because obviously the pitch information is lost. So all these sines take up, one wave cycle, and we can see these wave cycles by having a look at these little shapes here. That's the ramp, that's the triangle shape. But these are the only ones that are built into it. With the use of the amp input, we can create our own shapes that change the shape of the amplitude of each of these wave cycles. So how might we do that? First of all, there's two ways of doing it. There's an ugly way. Let's look at the ugly way first, which is attaching the pitch and the gate to a digital oscillator. And because we only want to multiply the signal by positives in order to create this envelope of sound, we only want to take the output. Well, we want to take the output from the unipolar, which is one side between 0 and 1. The regular output here goes between -1 and 1, and if we were to use that as the amp shaping window, the signal would be multiplied negatively and then positively, negatively then positively, which, if again, it's no problem with that. Why not do that? But in this example, clarity is key. So we only want to be shaping the signal in a positive way, as it were. So from 0 to 1. So we come out of the unipolar port from this mini oscillator. And let's see what happens. We need to put this back on none. So it's... let's just make sure nothing's happening there. So there is no amplitude windowing. So at the moment, we've got a shape up there. What's that? That possibly is a sine wave. So let's just flick through these and get to our saw wave shape, which we love and adore, and just make sure that's working properly. Yes, there you go. So that shape is being used to multiply the signal to create this structure. But as soon as I do something with the rate of the oscillator, in either of these oscillators, whether it's the Tangle Oscillator or this modulating oscillator, the volume modulating oscillator, they'll lose phase coherence, the cycles of the wave, even though now we're back on the same pitch because I put the course back on 0. Each parts of the wave cycle are slightly out of sync now, so it sounds different, and I can prove this by now letting go. Listen to this sound. I let go, and this is what the sound should sound like, but that click was introduced because of this crazy stuff, changing the relationship between the two signals. So this is the ugly way of doing it. Of course, there's advantages to this. You can stick it down an octave, have some fun like that. Why the hell not? FM that. Or stop me FMing that, I should say. So we'll put that back to course again. Back to 0, excuse me. And so that's a way of modulating the amplitude of the signal, kind of windowing this high frequency synced sine. The other way, which maintains phase coherence, is using the pos out. So this pos out here, as we can read the text, is loops between 0 and 1 in time with the frequency of the oscillator. So we can use that because at point 0, that will be the beginning of the wave, and at point 1 will be the end of the wave cycle. So we can use a modulation lane, is what I'm going to use this second, and we'll take the pos position out of there, stick it in the modulation lane, and stick the output in the amp as well. And right now, because the modulation lane is empty, there's no sound coming out. So if I lift this up, there you go, that's the signal. And we can create our own. Now that's our wave shape, our window. And because it's now synced, it's phase synced to the internal oscillator, we can do all this crazy stuff, and it stays. The amplitude signal and the oscillator itself maintain phase coherence. So, and of course, once we've done that, we can still apply all our crazy bending just switch to the engine mode. And of course, as we change this, we're changing. If you look at the scope, we can see the scope changing, going around so much. Change the amplitude shape of each of these wave cycles, obviously. And because it's internal, we're not running it after. This isn't happening after the oscillator. This is happening internally, so it's affecting all the FM and all this stuff as well. Anyway, I held that note down long enough. One other feature which needs to be mentioned is, so this knob, the repeat knob, I don't know if you saw that, but don't look too closely right now. So here we go. Repeats at 1, and we've got the repeat window mode set to off. In this mode, it's not, well, the repeat function is off. Instead, a push function has been sort of put here, basically. So as you can see, that's a sine wave, and it's, I mean, my crude description of it would be a kind of exponential pusher of the signal. I mean, technically, I think the technology is called a pusher, and there's a little bit of text in the pop-up on the repeat window. It describes it as a pushing style warp. The bend function is kind of mirror-like, so it's happening. There's a center point, and it's doing something from that center point outwards or kind of inwards towards it. And this push function is more of a kind of whole signal warping. I don't know if you can see that. It's kind of pushing the whole sine wave towards the end of the wave cycle. So if we look at that with a cosine, so it's just, you know, a kind of a sine wave with a slightly different harmonic set there. As we can see, there's a second harmonic there. We can push this towards the end of itself and it turns into a saw wave kind of shape with a bunch of even and odd harmonics to make it sound kind of rich and warm, and great for brass, great for kind of a kind of a tacky bit of a brass sound. Look, it's and we can shape it a bit more. This is all from a cosine. So this warping, this kind of pushing feature affects, like I say, well, I haven't said this, it affects all of the waveforms to a varying degree. So let's just resettle them again. And so that's what it does to a saw wave. That's the cosine, we've seen that. This is what it does to a triangle. It pushes it again to more of a saw wave kind of shape. Not exactly an algorithmically perfect saw wave, but it has saw properties, as you can see here, and kind of some harmonic little bump around there as well. Another cosine. When you mix the pulse with the signal next like the saw wave that sits next to, so there's a square and a saw wave next to each other. We bosh that around, push that around a bit, and then mix it back in with the square. You can use the pulse width to adjust that there. Some lovely wave shapes coming out of this. Look at that, lovely. Anyway, so that is the other feature. It's this push function that appears when you have the repeat window set to off. And I think that about covers everything. So I hope you found that mostly useful, and please put your feedback at the bottom of the video, and I hope you will make some use of these interesting sonic tools. Go off, make some noises, and thank you for watching.